not all are present here. Some of them were having problem. They were asking for, they are not able to connect. Last class we had done this problem, this one. Done. I asked you to solve this problem. I think we had gone out of time last class. So this was what your question? Mm, okay, what was the question? A pre-stressed concrete beam, 300 mm wide and 600 mm deep, is pre-stressed using 5 high-tension bars of 12 mm dia provided at 220 mm from the soffit of the beam. The effective stress in steel is 800 Newton per mm square. So find the bending that must be applied to the section to just avoid tension at the soffit of the beam. So, oh, you know these things like you have to calculate the. You know how you already know area section modulus BD square by 6. BD square by 6. Now the thing where you got problem maybe is in your pre-stressing force, because in the question it was given to you that the effective stress in the steel is 800 Newton per mm square. So we did not have the pre-stressing force here, but now pre-stressing forces were the force per unit area. No, sorry, this effective stresses we know it is force per unit area. So for the 5 number of tensile bars, this one 5 number of tensile bars and the 12 mm dia, we have the area is pi d square by 4 and your effective stress is this. So therefore your pre-stressing force will be obviously the stress into the area of the number of bars, 5 number of bars. So that gives your pre-stressing force to be 452,389 Newton. And now the what was mentioned to you, yeah, you're provided these bars were provided at 220 mm from the soffit of the beam. That means if from the soffit of the beam, so what happens is this is your section here. So here it is how much? 300. Here it is 600. So and your your center is supposed somewhere here. Hmm. So now this is your how much? This is your 300 mm. Now it is mentioned in your question that it is 220 mm from the soffit of the beam. Your bars are here. Oof, one now. This was your section. Here it was 300, 600. The center line was, suppose it is here somewhere. Then you were asked that this mentioned that at the soffit your tensile bars are provided here somewhere. Your bars are provided here somewhere. 5 number of bars. 1, 2, 3, 4, 5. So these are the 5 number of bars provided to you. At the soffit, from the soffit it is how much? 220 mm. So that means these are your bars. OP. Sorry for this circles that I cannot make it properly here. But this is how much from the soffit it is. This distance is here 220 mm. So that means we already know that our depth is how much? 600. So that means this total was to be 300 mm. The bottom part, half of this is 300 here, and above also it is 300. Here also it is 300 mm. So now in the question, 220 mm, your bars are at a distance of 220 mm from the soffit. Soffit means from the bottom it is 220. This distance is 220. So obviously now you can calculate your eccentricity, this one here. How much it will be? 300 minus your 220, which is your 80 mm. Okay. This is your 220 mm. This is your another 300 mm. Okay. So this is your eccentricity. In this way you can calculate E is your 80 mm. That means this distance is your 80. Your eccentricity of the tension bars are 80 mm. Right. So 80. Now in the question we were asked that find the bending that must be applied to the section. That means we have to calculate the bending moment because we don't know about the loads. It is not mentioned to us here. So we know the and also what it is to the section to just avoid the tension at the soffit. To avoid the tension at the soffit, that means at the bottom we have to calculate the stresses. So bottom we know it is how much? The direct stress is P by A. The stress due to bending is what? Plus minus M by Z, and that means at the bottom it is what? Minus M by Z. Plus minus, we know that. So minus M by Z, and due to this eccentricity, we were having minus plus PE by Z total stress at the total stress of the this particular beam now. So at the bottom, when we are considering at the bottom, we are finding out the bending, we are trying to find out the bending, this bending M here. So that means at the bottom, for the eccentricity, the moment, the stress due to eccentricity PE is what? Positive. Minus plus it was, so that means at the bottom it is plus compression due to this eccentricity. Okay, so now we know our pre-stressing force 45238 Newton, 9 Newton. PE eccentricity we know, section modulus you know, this one section modulus you know. So we can easily calculate, we can equate this and we can calculate our moment in this way. Okay, done. So not only moment in you may be asked sometimes to you may be asked to calculate the pre-stressing force when your effective stress, this effective stress will not be mentioned to you, and the number of bars will also not be mentioned to you. Then in that case, if you are given the loads, dead load, life loads you are given, so with the help of dead load and life loads you can find out the bending moments. So M will come out, eccentricity, section modulus, due to the from this section you will know the section modulus areas. But you may be asked to calculate the pre-stressing force when you don't have any hints of calculating the pre-stressing force, like the number of bars is effective stress, etc. So in that case, in that case what you will do, you will again equate it in in this way, whether it be, if you're asked in the top, it will be P by A minus PE by Z plus M by Z, and at the bottom it will be P by A plus PE by Z minus M by Z. This will give you your from this you can find out your either pre-stressing force, either your moment, or eccentricity if you want. In some problems you may be asked, so in this way you can equate and you can calculate the any things which you are asked for to find out. Okay, this is okay. Okay, understood this
Understand?
thing. Yeah, okay, now we'll go and find out. The next topic is our pre-stressing force, pre-stress beam at the bend tendons. In some, we also use bend tendons in some of the cases. Why? Because they give much more uh, what is that called, they'll counterbalance the load more as compared to the concentric or normal straight longitudinal tendons. In sometimes this are your bend tendons used, okay, which are at an angle theta with the horizontal, because what your this bend tendons are going to do, why we do that, because this bend tendons will provide this upward thrust, okay, which is going to counterbalance this external load which is coming. So by providing this bend tendon, what will happen, this upward pressure will be exerted on this concrete beam and will therefore counterbalance this external load. This figure you can see here, this bend tendon here, your pre-stressing forces will be applied here, this side, and this one here, this side. Okay, and this stresses, this bent tendons, the study of this bent tendons we can easily do for solving the forces by taking the free body diagram. Okay, free body diagram of the forces as you can see in this figure. So for suppose there is, this is suppose you are looking the free body diagram here, this is the load, upward load. Now due to this we will have an upward pressure of 2p sine theta. This, assume that this angle is at an angle theta, this your pre-stressing force, this one, array, your pre-stressing force, this pre-stressing force is at an angle of this theta. Okay, so what will happen now, the stresses, when you have a bent tendon, this is your W, so your net load which is now acting will be how much, this W total load minus your 2p sine theta, this one 2p sine theta. Okay, so what happens, due to the axial, you can see here, the for the beam the net downward load is this much, the axial longitudinal force provided by the tendon is actually P cos theta. If you see, it is P cos theta, because here we will have different means like this. So the vertical components will be your sine theta, p sine theta, p sine theta. So that is going to be your this 2p sine theta here. This one from the bottom it is going to come this side horizontal is p cos theta. So the longitudinal axis force provided is cos theta, which we can consider it to be p because the theta is very small angle. Okay, so if you see here, I want to show the diagram also. Yeah. Okay, see here. Now here was your bent tendon. Sorry, like this. this bend tendon here. So the direct stress will be now how much? We know it is force, the pre-stressing force divided by area. It is uniformly distributed load, direct load. So that is our P cos theta by A. But theta is very, very small, so we can consider it to be P by A. Okay, so now the net bending moment due to the external loads, this W, external load W, and also maybe the dead load will be there for the beam. So the moment will be how much for the dead load? The self weight of the beam is WL square by 8. We know, because this is your UDLs will be here, the self weight of the beam. Then we have the, due to this point load and the bend tendon, the effect of this bend tendon, the load due to the we know that for the point load, what is our, this one, what is our moment for the point load? It is W L by 4, W L by 4. We know the bending moment due to this point load is WL by 4, and our W is what? The total load W, this external load W minus, which is going to counterbalance your 2p sine theta. That is our total load. So this W is how much? Your now this W will be W minus your 2p sine theta. Theta. So let me write in this way theta. So theta. Okay, now WL by 4. That means again one L is going to be present there, which is your span. That divided by 4. This one. What was that? Our moment due to this point load was WL by 4, and our W is how much? Our W is W, this W total external load W minus 2p sine theta. Okay, 2p, hello. So that means what? 2p sine theta. So our total extra moment due to the dead load, or sorry, the point load is how much? W minus 2p sine theta into L divided by 4, which is this. Your moment, total moment now it will be this many moment due to this life load. Sorry, dead load, and the point load, which is external load, coming to be this much. Now we can, once we know the moments and the pre-stressing forces, we can find out the external.
Knock like it down. What's it?
Hello. Okay, extreme fiber stresses will be P by A plus minus M by Z. So, what is our P by A? We already know, you will know from the pre-stressing forces, and the moment, the stresses due to this bending moment, bending stress will be how much? Plus minus M by Z. M is this much, you know now. So, now this may be clear to you for the, when we use bend tendon, there is only this extra external force, which is due to this, which is trying to counterbalance some of the other external forces. When we do a bend, when we give bend to the tendons, why we give? Just to get this upward thrust, so that this outer thrust, so that this upward thrust can balance your external downward forces, which are coming on the beam. Okay, so now I think you'll be able to solve a problem also on this, because you just know that here in your bend tendon there is an upward pressure, the 2p sine theta, which is counterbalancing your external load, and there is nothing more on that. Okay, so we will try to solve now a problem on bend tendon. Note down this question. A pre-stressed concrete beam of 400 mm into 600 mm deep has a span of 6 meters. This span is given to us to be 6 meter. Okay, so this is 6 meter, the span is 6 meter, the dimensions are given to us to be 400 and 600. These are your dimensions. Deep has a span of 6 meter. The beam is pre-stressed with a tendon band as shown in the figure. This is the band tendon. The external load on the beam is 180 kilonewton. Okay, at the midspan, at the center, that means it is 180 kilonewton. If the effective pre-stressing force is 1200 kilonewton, that means this is the pre-stressing force. Here pre-stressing force is 1200 kilonewton. Calculate the extreme stresses. Okay, your dead load is calculated here. Dead load to be WL square by 8. WL square by 8. WL square by 8, that will give you your dead load to be 6 kilonewton per meter. Once you calculate, you will yourself know what is your dead load. Then we have this pre-stressing force 1200 kilonewton here, which is going to act here, is at an angle theta. We assume it to be at an angle theta. Also, okay. Also, in this figure, we are given that the tendon is placed at an eccentricity of how much? At least minus one, sorry,
1 foot and
140. Sorry, 140. So, from the question, we know what is our
from
eccentricity
the
here.
question we know what is our eccentricity.
Okay, from the question we know here that is our eccentricity here is 140. This one, this is 140. So you know your eccentricity, you know your this thing. Actually, this is not the eccentricity, but this is the distance of your this thing, the bend tendon, this distance. Okay, the center, it is shown that tendon bend here is from the soffit, it is 160 mm. So this distance is 140 here. So now this is your 140. So now calculate the, now what we are going to do here, since this is a bent tendon, we have to consider, here, if we consider this portion here, and consider that it is, we can calculate the this thing tan theta. What will be your tan theta if your pre-stressing forces at an angle theta, and here also you have these angles are your theta. So considering this, if you find out what is your tan theta, what will be your tan theta? And suppose I'm giving here theta to be in this way. Tan theta will be how much? Is it will be 140 by your how much? 3000, right?
without
So find out your tan theta. Okay. So we need what? 2p sine theta. We have to calculate the sine theta because we know our external load is 180 kilonewton, which is the W was 180 kilonewton, the external point load. Now we know that when we are provided with a bent tendon, there will be an upward thrust of 2p sine theta. So 2p sine theta, to calculate sine theta, we know that theta is very very small, so we can consider that to be your this one, tan theta. Since theta is very small, sin theta is very small, so we'll consider it to be tan theta. And so what you can now calculate, once you know your tan theta, you can calculate your this upward thrust, which was your 2p tan theta. Now you can write it to be tan theta, tan theta. Suppose this is theta. So now find out what is your 2p tan theta you will get from here. What is your 2p tan theta? Calculate.
112 kilonewton.
112 kilonewton.
Kilonewton.
Okay. Okay, then 112 kilonewton. I don't know the answer, but if you're getting, then it's okay. So 2p tan theta, that means this is the upward thrust. We got it to be this much. Now we can calculate the net uh, load. Net load will be how much? 180 minus our 112 kilonewton. So that will be how much? Calculate.
68 kilonewton.
68, yeah.
Good. So it is 68 kilonewton. That means this is our net load. Now we know our dead load to be this 6 kilonewton per meter. Dead load. Okay. We know our dead load is to be 6 kilonewton per meter, and now we know our after counterbalancing, what is our load which is acting on this point load, which is acting on the beam is 68 kilonewton. So now you know your point load, this one 68 kilonewton, and your dead load. You can find out the moments now. The total moment will be what? Total moment M will be your dead load plus your this point load. Okay. So the moment due to your dead load will be how much? WL square by 8 we know. WL square by 8, sorry, 8 plus our, what is this? The load which is acting now, it is 68 kilonewton. So it is how much? WL by 4. WL by, sorry, by 4. So find out this now. What is the total moment? You know your W. Dead load W is your this one 6 kilonewton. L span is your 6 meter 6000 mm. Then we have your point load 68 kilonewton. Your span again. So calculate this moment.
129 kilonewton meter.
129
Kilonewton meter.
So um, 1 minute. This one. Meeting is going to end in 5 minutes. Okay, whatever it is, let us now check the total load. See, so this is your calculation. See what we had calculated. We had calculated in. Am I audible? Too much of noises here. See, these are your calculations. See, the tan theta was this much. Your total upward force, it is 112. We got 112. Yeah, we got 112. Then the net upward was, we got this also correct. Bending moment due to the net, this much. How much you got? Your total bending moment, 129 kilonewton meter. Yes.
Yes, ma'am.
Yeah, okay. So we got, so now we know, once we know the total bending moment, what is our area, these things you know already, your section modulus BD square by 6, you know. Then you can now find out your total stresses developed at the top and bottom. Total stresses was what? P by A plus minus M by Z. Here is no eccentricity, so the stress due to the eccentricity is absent here in this case. Alright, so total stress will be how much? This one. P by A, it is 5 Newton per mm square. Your extreme stress due to bending moment is plus minus M by Z. M, you know, your total bending moment is this much, 129 kilonewton meter. So we got our top will be how much? Plus 5 plus 5.4. And at the bottom, what is your tensile stress will be 5 minus 5.5, which is 0. Minus 0.4 Newton per mm square. So it is done. Okay. Um, attendance now. Shall I take the attendance in second class or now I should take? Huh? Today's 31st. I'll do one thing. I'll just take a screenshot of where is my participants. This. I'll take the snapshot of this attendance. I'll give you in this way. Um, you all, whenever you're writing your names now, you just write your enrollments also at the corner, okay, so that it will be easy for me also then. If I take in this way, screenshot also. Himal. Okay. Now only the names are coming here. Login. Okay. So I will give you attendance in this way. I have taken. Okay. One more thing. Done this question. Understood this question? Hello. Hello.
Yes, ma'am.
Okay. You have noted this down. This problem.
Yes, ma'am.
Okay. Good. Very good. So one more question. Please try to. I give you this. Try to solve this question